I have a love-hate relationship with woodworking. Hear me out, I love seeing woodworking projects, but I absolutely hate trying to do it myself. And I think the biggest part of that hatred comes down to one thing. Right when you're almost done, you have this beautiful project completed, and yet now you have to sand the wood down to the final finish. And you sand and you sand and you sand for what seems to be weeks before that roughness becomes the thing you want. Now, this is exactly what happens when surfaces rub together and wear. We have a rough surface that's being eroded away by another surface, much like sandpaper on wood. And in many cases, like plateau honing, we're actually trying to create this surface, which has a texture being imposed on another. So today in this Notepad video, we're going to take a look at a different way of describing our plateaued surface. Let's look at the rough surface, like the wood of the table before we started sanding it. And let's look at this a little bit through the eyes of maybe mathematics. This surface has a distribution of heights. There's kind of a bell-shaped curve that represents where the points are. There are more points in the middle and fewer points out at the edges. This curve we call the amplitude distribution function in surfaces, but it's kind of a histogram. It tells us where things happen. And there's a lot happening around the middle of this surface. And when we see data like this in math, the way we describe this variation is often through the use of the standard deviation, or sigma. The standard deviation, sigma, is also kind of the RMS from electronics, and we have the parameter RQ in roughness as the standard deviation for this surface. Now, as we look at a surface, we might also consider where the material is, and we will plot a material ratio curve, or the bearing area curve. From 0 to 100%, we're going to calculate how much metal we encounter as we work our way down, and that will often be this S-shaped curve for a random surface like this. So a random surface has a standard deviation, has kind of an S-shaped material ratio curve. But let's go back in time a little bit. We didn't have calculators for many, many years, and in those cases, a graphical method where we would plot essentially the bearing area curve on special paper that's kind of bunched up in the middle around 50%, and then it spreads out at the edges. And if we move this curve to that kind of paper, we would get a single straight line for this random data. We've taken the bearing area curve to probability paper, and this is the material probability curve instead of the material ratio curve. It's still percentages, but the percentages are kind of messed up, and what we get is the slope of the line is the standard deviation of the data, or we can say the slope of the line is an RQ roughness. Now, this is beautiful for a single random surface. Let's add another random surface. We're going to plateau or wear our way into the surface. And this is a concept put forth by Williamson, the famous tribologist in the 1960s. And he showed that another surface moving through the original base surface is also random, and it would also have a straight line in this world. Now, we can look at this straight line also as an RQ. Let's call this the roughness of the peaks in the Q parameter family. And let's insert a V here, and we have the roughness of the valleys in this new Q parameter family. Our VQ number is actually calculated off just this tail end of the curve, RVQ, and it predicts the original roughness of the blue surface back here. See, once we're done, we only have the plateaus and the valleys remaining, and we would have this red part of the curve over here to work with, but it's enough to predict what the valleys used to be, and it gives us this intersection point where plateaus meet valleys, and this is the RMQ number. This RMQ number is important. It's powerful. If we rub away more material with the same peaks, we end up moving this plateau curve down, and we end up moving this line down, keeping the same RPQ in many cases, but moving our material ratio over. So the RQ parameter family gives us three numbers: a base roughness, a plateau roughness, and a position, just like our process of wearing or plateauing does for us. So to find out more about surfaces like this, or to have more discussion about what these Q parameters mean relative to the K parameters, or just better understand your surfaces, reach out to us at digitalmetrology.com. We'll be happy to help.